1. What is the difference between class and interface? A class is a blueprint that contains properties, methods, variables, and their actual implementation. We can create objects from a class and use its methods and properties. For example, a car class can have properties like color and model and methods like start and stop. An interface, on the other hand, is like a contract. It defines what a class must do, but it generally does not contain the actual implementation of that behavior. For example, an iCar interface can define start and stop, and a BMW class can implement those methods. The main difference is that a class provides the implementation, while an interface defines the contract that a class must follow. This infographic explains the difference between a class and an interface in C# side by side. Left side, class. A class is a blueprint that contains both data, fields, properties, and methods with actual implementation. The example shows a car class with color and model fields, plus a start method that has real code inside it, console, WriteLine, car started. When you use it, car C1 equals new car, you create an object directly, set its properties, and call start, which prints car started straight to the output, since the class already knows how to do the work. Right side, interface. An interface is a contract, it only declares method signatures without any implementation. The iCar interface declares start and stop, but provides no code for them. A class, BMW, then implements that interface using the iCar syntax, and it's the BMW class's job to actually write the code inside start and stop, printing BMW started and BMW stopped. When you use it, you can declare the variable as the interface type but instantiate it with the class iCar car equals new BMW, and calling car start and car stop runs BMW's implementation. Middle diagram shows the relationship visually. iCar only declares start, stop, and the arrow labeled implements points down to BMW class, which actually provides the code for those methods. Bottom comparison table summarizes the key rules. A class holds data and implemented methods. An interface holds only method declarations, no implementation, except static read-only fields. A class can be instantiated directly, new car. An interface cannot be instantiated directly. You always need a class that implements it. A class supports only single inheritance, one base class. A class can implement multiple interfaces, which is how C# gets around the lack of multiple inheritance. In short, a class is a concrete working object. An interface is a promise that a class must fulfill, enabling different classes to be used interchangeably as long as they implement the same contract. 3. What is method overloading versus overriding? Method overloading means having multiple methods with the same name in the same class but with different parameters, different number, type, or order of parameters. It is called compile-time polymorphism. Method overriding means a child class provides its own implementation of a method that is already defined in the parent class, with the same method name and parameters. It is called runtime polymorphism. In simple words, overloading equals same method name, different parameters, while overriding equals same method name and parameters, different implementation in the child class. This diagram compares method overloading and method overriding, the two forms of polymorphism. Method overloading, blue box, called compile-time polymorphism because the compiler resolves which version of the method to call at compile time, based on the argument types you pass. It happens within the same class. You define multiple methods that share the same name but differ in their parameters, different number, type, or order of arguments, like add, int a, int b, and add, double a, double b. Method overriding, green box, called runtime polymorphism because the decision about which method implementation actually runs is made at runtime, based on the actual object type, not the reference type. It happens between a parent class and a child class. The child provides its own implementation of a method that already exists in the parent, keeping the exact same method name and parameters, but changing what the method actually does. The arrow between the two boxes simply signals the natural comparison flow, overloading on the left, overriding on the right, not that one leads to the other. Bottom summary box boils it down to one line each. Overloading equals same method name, different parameters. Overriding equals same method name and parameters, different implementation in the child class. The core distinction to remember. Overloading is about choosing between multiple versions of a method in one class, resolved before the program runs, while overriding is about replacing a parent's method behavior in a child class, resolved while the program is running, based on the actual object. 4. What are the four pillars of OOP? The four pillars of OOP are encapsulation, abstraction, inheritance, and polymorphism. Encapsulation means bundling data and the methods that operate on it inside a class, while hiding internal details from the outside world, usually through private fields and public getter-setter methods, so other code can't directly mess with an object's internal state. Abstraction means exposing only the essential features of an object and hiding the complex implementation details, letting you interact with an object through a simple interface without needing to know how it works internally. Inheritance allows a child class to reuse and extend the properties and behavior of a parent class, promoting code reuse and establishing an relationship between classes. Polymorphism means an object can take many forms. The same method call can behave differently depending on the object calling it, achieved through method overloading, compile time, or method overriding, runtime, as we discussed earlier. This diagram lays out the four pillars of object-oriented programming, OOP, each feeding into the foundation labeled object-oriented programming. Encapsulation, blue, bundles data and hides internal state, meaning a class packages its fields together with the methods that operate on them, while restricting direct outside access, typically using private fields with public getters, setters, so other code can't freely manipulate an object's internal data. Abstraction, green, shows essentials, hides complexity, meaning you expose only the necessary features or interface of an object while hiding the messy implementation details behind it, so the user of a class only needs to know what it does, not how it does it, e.g., calling car start, without needing to know how the engine ignition actually works internally. Inheritance, orange, reuses parent class behavior, meaning a child class can inherit fields and methods from a parent class, avoiding duplicated code and establishing an relationship, e.g., a BMW class inheriting from a generic car class. Polymorphism, pink, one call, many behaviors, meaning the same method call can behave differently depending on which object is making the call, achieved through method overloading, same method name, different parameters, resolved at compile time, or method overriding, same method signature, different implementation in a child class, resolved at runtime. The arrows converging into object-oriented programming show that these four concepts aren't separate ideas, they're the pillars that, together, define what OOP actually is as a programming paradigm. Every well-designed object-oriented system leans on all four working in combination. 5. What is dependency injection? Dependency injection is a design pattern where an object receives the dependencies it needs, other objects or services, from an external source, rather than creating them itself internally. For example, instead of a class doing some service inside its own code, that service is passed in through a constructor, setter, or framework, so the class doesn't need to know how to build what it needs, it just uses it. This decouples classes from specific implementations, making code easier to test, since you can swap in mock objects, and maintain, since you can change implementations without touching the class itself, and it's the core idea behind inversion of control, where frameworks like Spring, Angular, or Netsd Container take over the job of creating and wiring up objects instead of leaving that responsibility to the classes that use them. This diagram illustrates how dependency injection, works, showing four moving parts and how they interact. Injector, DI container, top, orange. This is the external component responsible for creating and wiring objects together. It's the brain of the whole pattern. Instead of classes creating their own dependencies, this container takes on that job. Client class, bottom left, blue, the class that depends on a service to do its work. Notice it doesn't create the service itself. The injector hands it a ready-made instance, injects into arrow, which is the core idea of inversion of control. Service interface, middle, green. This is what the client actually calls the abstraction or contract the client programs against. The uses arrow from client to interface. The client only knows about this interface, not the concrete class behind it. Concrete service, right, red, the actual class that implements the service interface and does the real work. The injector is the one that creates this concrete object, that creates arrow from injector down to concrete service, and then supplies it to the client. How the pieces connect. The injector creates the concrete service. The injector injects that object into the client class. The client interacts with it only through the service interface. It never knows or cares which concrete class it's actually using underneath. Key idea, bottom box, the client never writes new concrete service itself. Instead, the injector hands it a fully constructed, ready-to-use object. This decoupling is what makes dependency injection so useful. you can swap in a different concrete implementation, like a mock for testing, without ever touching the client class's code, since the client only depends on the interface, not a specific implementation. 6. Difference between IEnumerable, ICollection, IList. IEnumerable is the most basic of the three. It only exposes the ability to iterate over a sequence of elements one at a time using for each via getEnumerator, and it doesn't know or care about the collection size, whether elements can be added or removed, or how to access an item by index. It's also lazily evaluated, meaning with LINQ queries the data isn't actually pulled until you enumerate it, which is memory efficient for large or streamed data but means you can't get a count without iterating the whole thing, except via extension methods that may enumerate internally. ICollection extends IEnumerable and adds more structure. It gives you a count property, without needing to enumerate, and methods to add, remove, clear, and contains items, making it suitable when you need to know the size of a collection and modify it. But it still doesn't guarantee any specific ordering or indexed access. You can't do myCollection, too, to grab the third element directly. IList extends ICollection, and therefore IEnumerable too, and adds indexed access, letting you get or set elements by position using myList, index, plus methods like insert and remove it for position-based manipulation. It's the richest of the three interfaces, so use IList when you need ordered, indexable data you can modify by position, ICollection when you need to know the count and modify the collection but don't care about order or indexing, and IEnumerable when you only need to read through data once, especially for method parameters, since accepting the most general interface your method actually needs gives callers maximum flexibility in what they pass in. This diagram shows the inheritance hierarchy of IEnumerable, ICollection, and IList in C#, going from the most basic interface at the top to the most feature-rich at the bottom. IEnumerable, top, gray, the base interface. It only supports iterating through elements with for each, that's it. It's read-only and forward-only, meaning you can walk through the sequence one element at a time in order, but you can't jump to a specific position, check the count directly, or modify the collection through this interface alone. ICollection, middle, green, extends IEnumerable. This adds more capability on top of basic iteration. A count property, so you know the size without having to enumerate everything, plus add, remove, and contains methods for modifying and checking membership. It knows size, and is modifiable, but it still has no concept of order or position. You can't access the third element directly. IList, bottom, red, extends ICollection. This is the richest of the three. It adds indexed access, meaning you can get or set elements by position, myList, too, plus insert and remove it methods for inserting or removing elements at a specific position. It's ordered and position-based, which is why arrays and list less than t greater than implement this interface. The arrows labeled extends show the inheritance chain. IList inherits everything from ICollection, which inherits everything from IEnumerable. So any IList is also a valid ICollection and a valid IEnumerable, meaning code that only needs to iterate can accept any of the three, while code that needs indexed access must specifically require IList. Practical takeaway. Choose the interface based on what your method actually needs. Use IEnumerable for simple read-through iteration. Most flexible for callers, ICollection when you need to know the count or modify the collection, and IList when you need ordered, position-based access. 7. Difference between ref, out, and in. Ref, out, and in are all C# keywords used to pass parameters by reference rather than by value, but they differ in intent and requirements. Ref requires the variable to be initialized before it's passed into the method, and the method can both read and modify its value. Changes made inside the method are reflected back in the caller's variable, making it useful when you want a method to potentially update an existing value based on some logic. Out also passes by reference and lets the method modify the caller's variable, but it doesn't require the variable to be initialized beforehand, since the method is expected to assign a value to it before returning, and it's commonly used for methods that need to return multiple values, like the tryparse pattern, e.g., int, tryparse, str, out int result. In is the most restrictive of the three. It passes by reference for performance reasons, avoiding a copy, especially useful for large structs, but is read-only, meaning the method receives a reference to the caller's variable but cannot modify it, giving you the performance benefit of pass by reference without the risk of the callee mutating your data. This diagram compares the three C# parameter modifiers used for passing arguments by reference: ref, out, and in. Ref, blue box. The variable you pass in must already be initialized before the method call. You can't pass an uninitialized variable. Inside the method, the code can both read the current value and modify it, and any change made is reflected back in the caller's original variable once the method returns. This is used when a method needs to update an already existing value based on some internal logic. Out, orange box. No initialization is required before calling. You can pass in a completely uninitialized variable. The trade-off is that the method is required to assign a value to it before it returns. The compiler enforces this. This is the pattern behind methods like int, tryparse, string s, out int result, which is commonly used to return multiple values from a single method call. One as the return value, success, failure, and one as the out parameter, the parsed number. In green box, like ref, the variable must be initialized before calling. But unlike ref, the method can only read the value, it's never allowed to modify it. This exists purely for performance. Passing large structs normally means copying all their data, but in passes a reference instead, avoiding the copy, while still guaranteeing the caller's data can't be accidentally changed inside the method. Bottom summary box. Why use each? Ref. Update an existing value based on logic inside the method. Out. Return multiple values from one method call. In. Avoid copying large structs without allowing mutation. The core distinction to remember. Ref and in both require the variable to already have a value, out doesn't. And of the three, only ref and out let the method actually change the caller's value. In is read-only, existing solely to skip an expensive copy. 8. What is async, await? Async, await is a pair of keywords in C#, and similar patterns exist in JavaScript, Python, and other languages, used to write asynchronous code that looks and reads like ordinary synchronous code, while avoiding blocking the calling thread while a long-running operation, like a network call, file I/O, or database query, completes. When you mark a method with async, it tells the compiler this method contains asynchronous operations and will likely use await inside it. The method typically returns a task or task less than t greater than instead of void or a direct value, representing work that will complete at some point in the future. The await keyword is then used before calling an asynchronous operation. When execution hits await, the method pauses at that point and returns control back to its caller, freeing up the thread to do other work, and once the awaited operation finishes, execution resumes from where it left off, picking up any result the operation returned, all without you having to manually write callbacks or manage threads yourself. This makes async, await especially valuable in UI applications, keeping the interface responsive while data loads, and server applications, allowing a thread to handle other incoming requests while waiting on I/O, improving scalability, and under the hood the compiler transforms your async method into a state machine that handles pausing, resuming, and exception propagation automatically. This diagram traces the execution flow of an async, await operation in C#, step by step. 1. Caller calls the async method. The flow starts with caller, which calls into the async method runs box. At this point, the method starts executing normally, just like any regular method. 2. Async method runs right pointing arrow hits await right pointing arrow starts a long-running task. As soon as the code inside the async method reaches an await expression, e.g., await some API call, it triggers the long-running task, like a network call, database query, or file read, to actually start. 3. Returns control to the caller. Here's the key behavior of await. Instead of blocking the thread while waiting for that task to finish, the method immediately returns control back to the caller, shown by the returns control arrow going down from async method runs. This is what makes async programming non-blocking. 4. Caller free to work. With control back in its hands, the caller isn't stuck waiting. It can continue doing other things, handling more requests, updating the UI, etc., while the long-running task runs in the background. 5. Task completes. Method resumes. Once the long-running task finishes, it signals back the long arrow from long-running task down to method resumes, and the async method picks up execution exactly where it left off, right after the await, with the result of that task now available to use. The core takeaway. Await doesn't pause the whole program, it pauses just that method and frees the calling thread to do other work, then automatically resumes the method later when the awaited task is done. This is what makes UI apps stay responsive and server apps able to handle many requests concurrently, without needing to manually manage threads or callbacks. 9. Difference between value type and reference type? A value type stores its actual data directly in the memory location where it's declared, typically the stack, though this can vary. meaning when you assign one value type variable to another, a complete copy of the data is made. The two variables are entirely independent, so changing one doesn't affect the other. Examples in C# include primitive types like int, float, bool, char, as well as struct and enum. A reference type, on the other hand, stores a reference, essentially a memory address, pointer, to the actual data, which lives on the heap. When you assign one reference type variable to another, only the reference is copied, not the underlying data, so both variables end up pointing to the same object in memory, meaning changes made through one variable are visible through the other. Examples include class instances, arrays, strings, and delegates. This distinction matters a lot in practice. Value types are generally faster to allocate and deallocate, since they don't need garbage collection and are cleaned up automatically when they go out of scope, while reference types require heap allocation and are managed by the garbage collector, and passing a value type to a method passes a copy, so changes inside the method don't affect the original, whereas passing a reference type passes a reference to the same object, so changes inside the method can affect the original object's data, unless the reference itself is reassigned.